Hello, my name is Bryce Peacock, and I'm an aerospace engineering sophomore.
Hi, my name is Keelan Fan, and I'm an aerospace and mechanical engineering junior.
Hi, my name is Diva Kanuja, and I'm an aerospace engineering junior.
This semester, we researched tailorable energy-absorbing beam lattices for advanced air mobility structures. Reinforced I-beam lattice structures have shown significant potential for lightweight energy-absorbing applications. Prior studies found that reinforced I-beam lattices can achieve over 200% greater energy absorption than traditional circular cross-section lattices. Most previous and reinforced I-beam lattice designs placed reinforcement only at the beam joints. This project expands on that idea by introducing additional reinforcements along the length of the I-beam, allowing the geometry to be modified to produce different mechanical responses. By varying the shape, spacing, and material stiffness of these sectional reinforcements, designers can tailor lattice behavior for specific applications. In this study, simple reinforcements were added along the beam, and materials with different stiffness values were used in separate lattice models to investigate how material selection affects mechanical performance.
Fabrication and material characterization. Multi-material I-beam lattice specimens were fabricated for compression testing. Different material combinations were then used to study material stiffness effects on structural response. Material characterization was performed to identify key mechanical properties. Characterized material properties supported interpretation of experiments and finite element modeling. As shown on the right, we printed the dog-bone samples, measured their mass, performed tensile tests on them, and then processed the data to achieve these stress-strain curves.
For finite element simulations, we began by making I-beams with reinforcements, merging multiple instances into a unit cell. Then we patterned that unit cell into a 3x3x3 lattice. To improve computational efficiency, we used shell elements and a quarter model for the quasi-static compression simulation. For the final element simulation results, we mirrored the quarter model into the entire 3x3x3 lattice. Here at the bottom, we can see the initial point of contact of the beams and successive steps down through the second densification.
Fabrication and experiments of lattices. Multi-material I-beam lattice specimens were fabricated with consistent reinforced geometries. Different material combinations were utilized to study their effect on the compression response. Compression experiments were conducted to evaluate stress-strain behavior and energy-absorbing crushing response. Experimental results were used to compare performance and validate computational analysis. Here at the top right are the three different material combinations for the lattices, and then here at the bottom are the various stages of the lattice compression test. Results and discussions. The lattices with stiffer material reinforcements demonstrated significantly improved energy absorption capacity. These high stiffness lattices bulged out at the sides more during the compression tests. This could explain the large peaks in the stress strain curves for the lattices composed of stiffer reinforcements. On the right are the experimental stress strain curves for the lattice structures.
In conclusion, sectional reinforcement and material combinations strongly influence stiffness, peak stress, and crushing response of multi-material I-beam lattices. Experimental results showed that reinforced I-beam lattices exhibit distinct mechanical behaviors and energy absorption capabilities depending on material combinations. Shell-based finite element models effectively capture overall trends and deformation modes. Discrepancies between simulations and experiments are expected due to the simplified shell representation of the printed structures. Reinforced lattice designs demonstrate strong potential as lightweight solutions for enhanced structural energy absorption. Thank you.